Hello everybody, I'm Muktikanta. This talk is about efficient Resumable Filter Queries. This is joint work with Pierre Sutra from Telecom South Paris. This is the outliner of my presentation. At first I'll give the motivation behind the work. Then I'm going to give how an operation can be resumed. Then what are the queryable data structure we are handling. Then I'll give some experimental results followed by conclusion and future works. Coming to the motivation, so consider a persistent data type or set which is accessed by multiple threads. And these multiple threads concurrently perform some operations like insert, get, remove, FQ nothing but the filter query. Insert is going to insert a new item to the set. Get is going to check whether the given item is present or not. Remove is going to remove an item from the set. So here it's filter query. It is going to iterate all the items present in the set and perform some filtering operation on them. We say filtering operation is long running because if the set contains millions or billions of records, filter query is going to iterate all the items and perform some filtering operation on them. So it is a long running operation. If there is no crash, then all these threads finish their operations in finite number of steps. If any crash occurs due to some power failure, then the problem arises for the filter query. As it is a long running process, so we do not save the results. So after crash, this filter query going to start the execution from the scratch. This is problematic for the industrial workloads like scan in TCP/IP. Now with these type of problems, so how we can able to resume the long running operations like filter query so that after a crash it should not start from the scratch, instead it should start just before the crash. Now coming to the state of the art, for the non-crashable execution we use the linearizability to prove the operations are correct. In this case each operation has a linearization point and its execution takes effect at that point. For the crashable execution, we use the durable linearizability to prove the operations are correct. In this case, each operation has a persistent point. So that is after the LP and before the response. So if we remove all system-wide crashes, then the operations are linearizable. But there is a problem with the definition of durable linearizability. A thread cannot be reincarnate, which means after crash, a thread never recovers. So this is not suitable for the long running operations where we explicitly want to continue the progress despite the failure. Now to make a thread can be reincarnate, we have to fix the definition of durable linearizability. So for that what do we did? So we stored the progress results in a durable state called resumption point, which is the generalized of persistent point. We say a resumption point is maximum if results of resuming after crash and without crash both are identical. So we also say a operation is resumable if all its resumption points are maximum. So with this definition, we are able to resume an operation after a crash. Consider an illustration. These are the multiple threads performing the concurrent operations. You can see thread T4 is performing the long running filter query. Also, you can see the progress results are stored in a durable state called a resumption point, like resumption point 1, 2, 3 up to 8. After 8, the system make a crash. Then we invoke the recovery procedure. After recovery, this filter query resumes its operation just after the resumption point 8 instead from the scratch. So this saves a lot of time because the results already computed. So after crash, instead of starting from the scratch, we start the execution just after the resumption point.
Coming to the representation of queryable data structure, this representation is for list. The skipped list and the hash table representations are similar. The data structure is divided into two memory areas, one for volatile memory, another is for non-volatile memory. The nodes which are present in the volatile memory, they are similar to the T-memory's log-free linked list. So each node has a immutable key field and word size pointer nest which hold the address of the nest pointer, and as a pointer ptr which hold the address of the node is present in the non-volatile memory. And these list nodes are linked by the nest pointer. They are separated by the head, two sentinel nodes head and tail. The, the nodes which are present in the non-volatile memory, it is same key value as node present in the volatile memory. It is two boolean plugs, I plug and D plug. They represent whether the node is inserted or deleted or in middle of the insertion or middle of the deletion. So there is a field called FQ which stores the results of a filtering operation which is performed by the filter query operation. And there is also two fields of the ITS and DTS. They are the insertion timestamp and deletion timestamp. So they are recorded from the values of the global timestamp, and this is handled by the filter query operations. It stores the ITS nothing but the store the insertion time, and DTS store the deletion timestamp. So initially, if there is no filter query is going on, the ITS value is 0 and DTS value is -1. So when any filter query is performed, it is going to increment the global timestamp. Based upon the global timestamp, the insertion time and deletion times are recorded while performing the insertion and deletion. There is two other global variables that you can see. There is RP is the resumption point, and in the D is the list of the deleted nodes. The resumption point, anytime the filter query performs the filtering operation on the node, it updates the FQ field. At same time, it is going to store the resumption point. So any crash occur after the recovery, if the filter query going to resume its operation from that RP. And the field D, it is a durable set. All the deleted nodes are kept in the durable set D. So once the filter query finishes its operation, before returning, it needs to clean all the D nodes. We have implemented four persistent data type operations: the insert, remove, get, and filter query. Insert, remove, get, they are based upon the Jurel's durable linked list and T-Mary's lock-free linked list. So whereas the filter query operations is based upon a wait-free iterator by Pattern and Timnan. Now coming to the working of the operation, consider a state where my PDTs look like this, and green thread wants to insert 7, yellow thread wants to remove 5, and red thread wants to perform the filter query, which is the square sum of the all key value. To insert or remove an item from the PDT, we follow the traditional log-free pattern. So a green thread wants to insert 7. At first it traverses the list and find the location. After that it checks whether the key is present or not. If that key is not present, then it creates a new node in the volatile memory and its corresponding non-volatile node, and then it try to insert that node using case. If case failed, it retries the operation again. Similar for the remove, at first it finds the location, and if the key is present, it try to mark that node logically. After that, it move for the physical deletion. compared to the optional durable linked list, our list operations has two key differences. When a thread traverses the PDT, it helps ongoing insertion or removal operations. Second, when an insertion or removal operation see that there is an ongoing filter query, they tries to help filter query. If it is an insertion operation, it helps filter query by computing the filtering operation and store the result in the FQ. We will see how the remove operation helps the filter query in the next slide. Now coming to the filter query, if a thread wants to execute a filter query, at first it increments the timestamp. Then it moves through a two passes to get the correct result. In the first pass, it iterates all the nodes and compute the filter query, store the result in the FQ. And in the second pass, it collects all the results which is already computed in the first pass. Now we will see how a remove operation is going to help the ongoing filter query operation and why we need a separate durable set Thomson D. When a thread performing a remove operation, it notices that there is an ongoing filter query. Any thread wants to remove a node, so after removal, they need to put that node in a durable set called Thomson D. If we are not adding the deleted node in the Thomson set D, what problem we are going to face? Let us consider a scenario where yellow thread wants to remove 5 and red thread is performing the filter query. So as I said, filter query passes through two phases. In the pass one, it iterated all the nodes present in the PDT and compute the filter query below. So in the first one, it check yes pipe is the part of the PDT, so it computed and stored the value in the FQ. So after finishing the pass one, the filter query moved for the pass two. The time to it going to collect the results. In that, start collecting the results and check yes pipe is also part of the PDT, so it is collected. In time, the yellow thread came and removed the pipe and inserted a new node. If the deleted node is not added in the set D, then it is problematic for the filter query, because in the second pass it checked that pipe is part of the PDT, so it is collected. Before it finishes the collection, somebody came and removed that node. Pipe is not part of the PDT, but the filter query thread is getting the filter value of the node 5, which is incorrect. So to fix this problem, after collecting the filter query results, a red thread has to move through the set D and checks what are the keys which are present and they are the part of the results. It need to discard all of them. Then it returns the correct results. This way, Thomson set it helps for the getting the correct result. Now coming to a filter query with a crash. So anytime the filter query computes the filtering value and stores in the FQ, that time it refers that node to be resumption point. So whenever any crash occur after the recovery, filter query operation going to resume from that point. So you can see, so after computing the node 9, it made a crash. So after crash, it is going for the recovery. In recovery, after constructing all the data structure, the filter query operation going to resume from that point. So now it is going to start computing the value for the node 10 and move forward. Coming to the experimental results, we implemented our PDTs in an Intel quad-core system which has dual socket and it has 80-core system. But we pin all the threads in a single socket. It has 128 GB volatile memory and 512 GB of non-volatile memory. All the code are implemented in C++, is around 8,000 lines of code, but we don't use any garbage collection. For the non-volatile memory, we use the Intel PMTK library. For the multi-threading purpose, we use the pthread. So we use the NVM in the app direct mode, which is formatted with the DX mode. For the benchmarking, at first we load half of the million items in the PDT. Then we perform around 1 million of code operations get, insert and remove with some distributions. For the filter query, it is run by single thread concurrent with the code operations. So we explicitly made a class after filter query covers half of the elements, and then after recovery it finishes the execution. Once filter query finishes the execution, all the threads stop executing the other operations. Now coming to the performances, we took three workload distributions. One is first one is lookup intensive, that gets 90% get and 5% is for the insert and remove. And another case is equal update and equal lookup, that gets 50% get and 25% is for the insertion and removal. For the update intensive, the 10% is get and 45 each for the insertion and removal. We compare these two cases. First one is volatile case and other is PDT case. For the volatile, everything in the volatile memory. And for the PDT, the both P node and thumbstone D set are in the non-volatile memory. This is the performance for the skip list. We have all three cases, the lookup intensive, and this is the equal lookup and update. This is the update intensive. So what do we observe? Persistent skip list is slower than the volatile counterpart. This is expected because volatile memories are very faster than the non-volatile memory. So what we observe then, across all the workloads, on an average, we are just 5 to 10% slow. This is the performance result for the hash table. We have three workloads. So lookup intensive. This is the equal lookup and update. This is the update intensive. So what we observe, the persistent hash table is slower than the volatile counterpart, which is expected across all the workloads. On an average, we are 20 to 25% slow. But what we observe that if the number of threads are increasing, the performance gap between volatile and non-volatile is increasing. This is not true for the skip list. So honestly, we don't know the reason as of now. We are in the initial stage of evaluation. We are analyzing the results. Hope we are able to come up with a concrete reason for this. Now coming to the resumable filter query, we took this is the distribution, the 80% get, 20% is insert, and filter query is run by the single thread. We compared the following cases in the persistent version of a skip list. So in that case, both P node and thumbstone D set are in the non-volatile memory. For the volatile skip list, everything in the volatile memory. For the file system skip list, both P node and thumbstone D set are in the non-volatile file system. For solid state drive skip list, the both P nodes and D set are in the SSD file system. And similarly for the hash table also. PDT version of the hash table, volatile hash table, file system hash table, and SSD hash table. This is a result for the resumable filter query with a crash. We recorded the execution time before crash and how much time it takes to recover and how much time it takes to finish the execution after the crash. We have all four cases for the skip list as well as the hash table. And we made the crash once the filter query covers around half of the items in the list. Then what we observe that PDT version of the skip list is 40% is faster than the volatile version. So whereas PDT version of the hash table is 16% faster than the volatile version. And both the cases they are
faster than the file system, whether the file system is implemented in the NVM or it is implemented in the SSD. In conclusion, what we observe that durable linearizability is inadequate for the long running operations. To fix the definition of durable linearizability, we come up with a notion of resumable operations with maximum resumption points. With that, we implemented various PDTs like skip list, hash table with support of resumable filter query. In the future, we want to use this technique for the different data stores and we want to compare the results with real world workloads like YCSPE, OLAP, etc. That's all. Thank you very much.